Lecture 1 is Structure and Synthesis of Alcohols. This is going to be the first half of our tour of alcohols, which is split between chapters 10 and chapter 11 in Wade. We're then going to do a short chapter on ethers, epoxides, and sulfides before changing gears for a bit and spending a couple weeks on spectroscopy. After spectroscopy will be our midterm. So these couple chapters here involving alcohols and involving ethers, epoxides, and sulfides are really the only reaction-centric chapters that we're going to cover in the first half of this semester. Up until this point, we've been looking at how to make and use the various functional groups as we cover those functional groups. We started with halogens, so chlorine and bromine, for example, on some alkyl group. Those are generally made by free radical chain reaction, and we use them in nucleophilic substitution and elimination. We then moved on to alkenes, the carbon-carbon double bond, where we made them by elimination and used them in electrophilic addition and oxidative cleavage. We then finished up the first half of Chem 304 using alkynes, the carbon-carbon triple bond, that we made by double elimination and can be used in electrophilic addition similar to alkenes, oxidative cleavage similar to alkenes, but we added acetylation, which was our first tool to make carbon-carbon bonds. Today we're adding another functional group, which we're already kind of familiar with because we've made them before, and that's the alcohol, which is an OH group attached to some alkyl chain. So I like to think about alcohols as probably the most useful functional group. I say in the title slide, the most functional group. You can do so much things, so much stuff with alcohols that they're a great place to start. That oxygen is a very, very useful atom because of its dynamic bonding characteristics. So let's look at water for a moment. Water is not strictly an alcohol because it's not an organic compound, but water and alcohols have very similar properties. Normally, water has a bond angle of about 104.5 degrees. The oxygen is sp3 hybridized with two lone pairs. That pinches the bond in a bit. We've got a kind of 3D picture here, as well as the electron potential map of water. If we compare it to alcohols, we've got the same kind of structure as water, except that one of the H's will be replaced by some alkyl group. In this case, it's a methyl group. Because of the bulkiness of the methyl group, this bond will not be pinched quite as much. Obviously, you can see it's 108.9. That's a little bit less than 109.5. So this oxygen having two lone pairs on it does cause this bond to be pinched a little bit more than you would expect for an sp3 hybridized atom. You can see that the bond lengths are different. These oxygen-hydrogen bond is quite small compared to a carbon-oxygen bond, which is a little bit longer. Not quite as long as a carbon-carbon bond, but a little bit. The more polar a bond, the shorter it tends to be. We would call this maybe methyl alcohol. It's an alcohol group with a methyl on it, and we can see the electron potential map kind of has the same electron distribution. We've got all the electron density up on the oxygen, and we are missing electron density, meaning we've got positive character on kind of the bottom half of the molecule. You'll notice that there's quite a bit of positive character on this hydrogen. That's because it's a polar hydrogen. There are two polar groups on an alcohol. First of all, there's the polar carbon-oxygen bond, and there's also a polar OH bond, and that is an acidic hydrogen. When we talked about polar protic solvents, an alcohol was exactly what we were talking about. It's very polar. We've got a negative end of the molecule and a positive end of the molecule, and we've got an acidic hydrogen, so it's protic. Because of that, alcohols can participate in hydrogen bonding. That causes their physical properties to be quite a bit different than a lot of the organic structures that we've seen so far. Because of the hydrogen bonding, they tend to have higher boiling points, higher melting points. They tend to be more water soluble, things like that. Alcohols are relatively acidic. Most alcohols have a pKa of about 16 to 18. That varies minimally depending on the substitution of the alcohol, which we use a similar terminology that we've seen for hydrogens, for alkyl halides, and for carbons, the primary and secondary and tertiary designation. Now, in an alcohol, the oxygen is always going to be attached to one carbon. So it doesn't make sense to talk about an alcohol as being primary because all alcohols will be primary. All of them will have one carbon on them. So what we mean by a primary alcohol and a secondary alcohol and a tertiary alcohol is really the substitution of the carbon to which the alcohol is bonded. So on our primary alcohol here, the carbon bearing the alcohol has one other carbon attached to it. In the secondary alcohol, the carbon bearing the alcohol has two carbons attached to it, 1, 2. In the tertiary alcohol, the carbon bearing the alcohol has three carbons attached to it, 1, 2, 3. That's similar to what we looked at for alkyl halides. We talked about primary bromines, secondary bromines, kind of like primary leaving groups, secondary leaving groups, tertiary leaving groups, and that determined SN1 versus SN2 conditions, for example. We can have a benzylic alcohol, meaning the alcohol is on a benzylic carbon rather than, say, a tertiary carbon. It's a benzylic carbon. We could also have, say, an allylic alcohol. We've seen allylic groups before. Benzylic is kind of like primary. The carbon bearing the alcohol has one carbon on it. So the degree of substitution is similar or kind of analogous to a primary alcohol, but because of that benzene ring, that gives that bonded carbon unique properties. Now, phenol is a special alcohol. This is phenol. It's basically a benzene ring with an OH directly attached to it. Sometimes it's called phenyl alcohol, PHENYL, phenyl alcohol. We learned about phenyl groups in the alkenes chapter. This is phenol. It's basically a phenyl alcohol. It is much more acidic than other alcohols, about 1,000,000 times more acidic, has a pKa of about 9.5. The reason why phenol is so acidic is because the conjugate base, that is to say, the anion that is formed when phenol loses its alcohol hydrogen as an H+, is resonance delocalized. You can delocalize that negative charge from the oxygen to 3 other carbons in the ring. Now, obviously, the negative charge on the oxygen is better than a negative charge on any of these carbons. So the predominant resonance structure will still be the structure that has the negative charge on the O. But simply being able to delocalize that charge a little bit onto 3 other atoms makes that negative charge way more stable than it would normally be on an oxygen, which is already pretty good. This is an electron potential map of phenol. Actually, this is the phenoxide ion. So this is the ion that you get by removing the H+ from phenol. It's this. Now remember that all the resonance structures really just represent different ways to view a single structure. So you can see that this electron potential map, most of the negative charge is on the oxygen. That's what we would expect because we would expect this resonance structure to be the major contributor. But you can also see that there is significant negative character on these 3 other carbons, and those are the 3 carbons that bear a negative charge on the other resonance structures. These are minor contributors. That's why we see less electron density on them. And this is the major contributor, which is why we see more electron density on the O. Like I said before, we've used other molecules to make alcohols previously. Here are some examples of other reactions that we've seen that created alcohols as the product. We could use nucleophilic substitution from any alkyl halide using hydroxide as our nucleophile. You displace the halogen and you get an alcohol. We did hydration using H2O and H3O+, so acidified water. Hydration of an alkene was Markovnikov addition of an alcohol. Also oxymercuration, demercuration. was Markovnikov addition of an alcohol. We did hydroboration oxidation, which was anti-Markovnikov addition of alcohols. We did syn dihydroxylation, which was OSO4, osmium tetroxide, and hydrogen peroxide, or KMNO4 cold, neutral conditions. We also did anti-dihydroxylation, which is where we first made an epoxide by using MCPBA, and then we opened the epoxide under acidic conditions or basic conditions, and that gave us anti-diols. So all of these 5 methods for making alcohols were based on alkene chemistry. We also made alcohols by addition of acetylides to carbonyls. Remember when we created that carbon-carbon bond by using our acetylide as a nucleophile to attack the carbon on the carbonyl? The pair of electrons that left the carbon was the pi electrons, and those went onto the O to make an O-, which we would then protonate to make the OH. If you don't remember that, go back and look at Chapter 9, Lecture 13 from Chem 304. That I put in red because that was the first way that we ever saw of making carbon-carbon bonds. Related to that, I want to talk about organometallic compounds. This is another way, now our second way, of making carbon-carbon bonds. And we're also going to use carbonyl groups as our main electrophile, which means we're also going to be making alcohols along with that carbon-carbon bond. So organometallic compounds are organic compounds that contain a covalent bond between carbon and a metal atom. That's pretty rare. Metals don't generally like to make covalent bonds. They are quite electropositive, and so they like to create ions and therefore make ionic bonds. So making covalent bonds between carbon and metal is a pretty rare thing. They're quite a unique type of group. They are useful. I will show you in a minute that we make nucleophilic carbon atoms, in contrast to what we normally have, which are electrophilic carbon atoms, usually attached to alkyl halides or attached to carbonyls. Those are electrophiles, but organometallic compounds give us a carbon nucleophile the same way or in a similar way that acetylides did. Now, why do we get that? Most metals are more electropositive than carbon. And so if you have a carbon-metal covalent bond, it will be a polar bond, and it will be polarized with the positive charge on the metal and the negative charge on the carbon. That's opposite of what most polar bonds that we've seen so far. Most atoms to which carbons have been attached have been to the right of carbon on the periodic table, like nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All of those are more electronegative than carbon, which means that in all of those polar bonds, carbon has been positive. But compare the electronegativity of carbon to some other metals. Aluminum 1.6, magnesium 1.3, lithium, sodium, potassium around 1. Those are significantly more electropositive than carbon. So when we have that carbon-metal covalent bond, the polarity of the bond is reversed from what we're normally used to. That puts significant negative character on the carbon and makes it very nucleophilic. Here's how it works. If you start with an alkyl halide, some RX bond, so where X, of course, is chlorine, bromine, or iodine, which, by the way, we know how to make. We know how to make lots of alkyl halides, like taking an alkane and doing free radical halogenation, or taking an alkene and doing Markovnikov or anti-Markovnikov addition of HBr, for example. So lots of ways that we can already make an alkyl halide. Then all we need to do is take that alkyl halide, react it with magnesium or some other metal in diethyl ether, some polar aprotic solvent. Being aprotic is very important in this case. We'll talk about why at some point. So some polar aprotic solvent like diethyl ether. And what the metal will do is it will oxidize from magnesium 0 to magnesium 2. and it will make two bonds. It will insert itself between the R, between the alkyl group and the halogen. That is a labile CX bond. This is a reactive bond, and magnesium can insert itself between the R and the X. Remember, magnesium is in the second column of the periodic table, which means that it makes a 2+ ion, which means that it's got room for two bonds. So that's why it inserts itself between the bond so it can make two. So, for example, if we have methyl iodine or iodomethane, here's our polar carbon iodine bond. We react it with magnesium in ether. The magnesium inserts itself between the carbon and the iodine, and you see that it reverses the polarity. Here, the iodine is negative and the carbon is positive. Here, when it inserts the magnesium, well, the I is always going to be negative, but now the carbon is being negative. This is so unhappy, this carbon is being negative, that you can basically think of it being as an R- with a lone pair and then an MgX plus. You can basically think about this R-Mg covalent bond as being so very, 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 very extremely polarized that it might as well be a full R-. These are called Grignard reagents. That's pronounced Grignard. These RMgX carbon nucleophiles are called Grignard reagents. Grignard reagents are super cool because you can make Grignards from just about any alkyl halide. They can be primary, they can be secondary, they can be tertiary, they can be allylic, they can be benzylic. It doesn't matter. Any alkyl halide refluxed with magnesium in ether will make the alkyl magnesium bromide. You see here that magnesium has inserted itself between the bromine and the carbon that the bromine was bonded to. That gives this carbon right here, the carbon bearing the magnesium bond, significant negative character, and that becomes our nucleophile. Here's another example, allyl bromide, an allyl group. Here's our carbon bromine. We're going to react it with magnesium in ether. The magnesium is going to insert itself between the carbon and the bromine, and lo and behold, we will have a negative charge or a significant partial negative charge on this carbon. There's another brand of organometallic reagents called organolithium reagents. This is basically the same thing that we just saw with Grignards, except we use lithium as the metal instead of magnesium. It's a slightly different recipe. Because magnesium can make two bonds, but lithium can only make one bond, we need two equivalents of lithium to get the same effect. The RX bond, instead of getting inserted by the metal, will split and you will get the lithium plus with the X minus. So one of the lithiums is wasted, but the other lithium will be covalently bonded to our R group. And again, that bond is so polarized with the negative charge towards the R that it reacts as if it were R minus with a lone pair and Li plus. Organolithium reagents are functionally the same as Grignard reagents. I don't care if you use one over the other. As you see here, lithium, you can make a lithium reagent bonded to carbon from a primary group. Here they're doing it on a sp2 hybridized carbon, a vinyl chloride, which gives you an sp2 hybridized carbanion. That's something we haven't seen before. Here's another one where our carbon is sp2 hybridized to a bromine. We've got two lithiums. The lithium is going to bond to that carbon. The other lithium will go with the bromide, of course. So now we've got another sp2 hybridized carbanion. Again, all kinds of ways to make carbon nucleophiles. All you need is a halogen attached to your carbon. All you have to do is add lithium or magnesium, and that carbon will become nucleophilic. It's that simple. Then all you need is the choice of the proper electrophile. You can use your organolithium or Grignard reagent as a nucleophile, with any electrophile of your choice for the most part. One very popular electrophile for addition of organometallics is the carbonyl, which is what we saw when we did acetylide chemistry. You can create a carbon-carbon bond by using the carbonyl as the electrophile and simultaneously generate an O-, which then if you add water or a little bit of acid at the end, will protonate the O and you get an alcohol. So again, we are making alcohols. That's the point of this chapter. You can use ketones as your carbonyl source. You can use aldehydes. Formaldehyde is a great choice. Having two H's on that carbon makes it very, very accessible. These are not bulky groups. So that carbon pi antibonding orbital is quite accessible if those are hydrogens. That's formaldehyde. You can see there's a lot of positive character on that carbon. Here's a synthesis problem that I'd like you to try on your own. I want you to show how you would synthesize this alcohol starting from some starting material of your choice, but the book gives you this limitation. The book wants you to use compounds that contain no more than 5 carbon atoms. So you'll notice that we've got 5 carbons on the ring, plus another 4 carbons outside of the ring. So don't use a large molecule here that contains more than 5 carbons. Your pieces have to contain 5 or fewer. Now, after you solve this, starting from compounds containing no more than 5 carbons, there are 2 other ways you can do it. That removes the limitation. If you can do it 2 other ways using molecules that have more or less carbons. So see if you can find 2 more ways to do it, ignoring this arbitrary limitation of no more than 5 carbon atoms. Give it a shot. We'll go over it in lecture. I have a note that shows the retrosynthetic analysis of this molecule and kind of shows the logic of how you decide where you want to start to get here. There are 2 classes of carbonyls that I call special carbonyls, and those are the acid chloride, shown here, and the ester, shown here. An acid chloride is a carbonyl group, the C double bond O, where our carbon bears a chlorine. Sometimes it's just called an acid halide, because this chlorine could be a bromine or an iodine. Usually it's chlorine though. So that's the acid chloride. This is an ester where the carbonyl carbon has an OR group on it. The reason I call these special carbonyls is because when you have a Grignard nucleophile or a lithium reagent nucleophile, remember those are interchangeable, you get double addition to our carbonyl carbon. Notice that if we have 2 RMGXs and 1 acid chloride, our reaction product has 2 additions of those R groups. That by any chance gives us a tertiary alcohol. This R prime group is also a carbon. So double addition to the acid chloride. Same thing with the ester. If we have 2 additions of Grignard, it will add twice. By the way, if you try to control this by only using 1 equivalent of Grignard, you will get double addition anyway. You'll just end up with some molecules that don't react at all. So there's no way that you can control this using stoichiometric limitations. You will always end up with double addition to these guys. So why is that? Let's look at a mechanism. Here's the addition of organometallics to these special carbonyls. The first step should be familiar to us. The R group acting as a nucleophile with its bonded electrons being the nucleophilic electrons. Those are going to attack the carbon and kick off the pi electrons onto the oxygen. That gets us this intermediate where we've added 1 of our R groups. But what's unique here is that the chloride is a pretty good leaving group already. It's not as good a leaving group as the pi electrons. Notice that, remember, the pi electrons are higher in energy than sigma electrons. So if we're going to choose two electrons to leave, we're going to use the highest energy electrons, which are the pi electrons, instead of the sigma electrons. So that's why we get this structure here. But chloride is a good leaving group. So what happens is this tetrahedral intermediate collapses. These electrons come back down off the oxygen, but rather than kicking off an R group, which are terrible leaving groups, we kick off the chloride, and that gives us a ketone. Now we've regenerated our double bond, which means that if there is any other Grignard around, which of course there will be, you're going to get another addition of that Grignard to our ketone. Ketones are susceptible to attack by a nucleophile. So our Grignard will add to the ketone, kick the electrons back up. Now we've got two of our R groups added from our two equivalents of our Grignard. And at the end, we just add a little bit of acidified water and we get our alcohol. So don't forget that. Keep that in mind. Anytime you are doing addition of a Grignard or lithium reagent to an acid chloride or an ester, the Grignard or lithium reagent will add twice, first displacing the chloride or the OR group, depending on if you have an acid chloride or an ester, and then regenerating the ketone, and the second equivalent adding back to the ketone. So we have two additions of our R group. Another popular electrophile that is paired with organometallic reagents is the epoxide. Remember, in the reactions of alkenes, we used epoxides as electrophiles, where we opened up the ring by attacking with either water under acidic conditions or hydroxide under basic conditions to open up the ring and get di-alcohols. We could get anti-diols by opening an epoxide. You can also open epoxide with organometallics because they too are strong nucleophiles. One thing to remember though, when you add organometallics to epoxides, is that organometallics are incredibly basic. That R group has a very, very strong negative character to it. And so, as we saw before, addition of base to an epoxide will always occur from the less substituted carbon. So in this case, notice that we have a symmetrical epoxide, but it could be asymmetrical. In this case, it's a symmetrical. We'll just show the R group adding to one of the carbons. If it's asymmetrical, it'll always add to the less substituted carbon. That's going to open up the ring. That's going to put the R group on one carbon and the O- on the adjacent carbon. We will then finish the reaction just by adding a little bit of acidified water, and we will end up with our protonated alcohol. Don't forget that you can always make an epoxide from MCPBA oxidation of an alkene. Now, there's a certain pattern here that I want you to pay attention to. Notice that the alcohol is on the carbon adjacent to the carbon that our nucleophile attacked. That is different than what we saw with the Grignard or organometallic addition to a carbonyl. In Grignard or organometallic addition to a carbonyl, the alcohol is on the carbon that was attacked. In this case, it's been attacked twice already, but we have our R groups on the carbon bearing the alcohol. That's what we saw anytime we added to a ketone. We saw that with acetylation as well. So this is a slightly different pattern. Here we have our R group on a carbon adjacent to the alcohol that created. So if you are paying close attention to the arrangement of things in your product, you can say, aha, I want to put this R group on, and I want to put an alcohol on, and I want them to be on adjacent carbons. We can do that by opening up an epoxide with our R group nucleophile. Keep that in mind. Instead of using C- nucleophiles, like we are doing with organometallics, organolithium, Grignard, and acetylides, We can also use hydride as a nucleophile. Hydride is H minus. Hydride we've seen before. We used hydride with sodium hydride, NaH, to deprotonate an alcohol and make it into an alkoxide, make a weak nucleophile into a strong nucleophile. Hydride's a pretty nasty base. It's a really good base. It can also be a nucleophile. It's small, it's highly negative. The charge ratio is we've got twice as many electrons as we have protons in the nucleus. So it's got a high charge ratio that makes it a good nucleophile. So we can use it the same way that we use, say, Grignard's or lithium reagents. We call it a reduction, though, because we are increasing the number of hydrogens bonded to carbon, and we are decreasing the number of oxygens bonded to carbon, the number of oxygen bonds to carbon in this process. So the same way that we added any other nucleophile to a carbonyl, we'll add the hydride. The electrons will add into the pi star antibonding orbital that will cause the pi bond between the C and the O to break. The electrons will go onto the O because it's more electronegative. We have created an additional bond from carbon to hydrogen, and we have lost a bond from carbon to oxygen. So that by definition is a reduction. Usually after the reduction, we'll end up with that alkoxide, and as usual, we can just add water or a little bit of acidified water, perhaps acid, to protonate our alkoxide and make it into an alcohol. Hopefully you're noticing that a lot of these reactions, again, if we have an alkoxide, a negative charge on an O, sometimes even on a C or an N, usually you will finish the reaction by adding some protic solvent so that all of our anions end up getting protonated. Where do we get hydride from? Obviously, you can't bottle hydride, but you can get hydride from NaBH4, sodium borohydride. We've used that before in oxymercuration, demercuration. Or you can use lithium aluminum hydride, LiAlH4. Both of these have the group 3 atom, the boron or the aluminum, attached to 4 hydrogens. That makes the B negative and the aluminum negative, and those are then paired with the positive sodium or the positive lithium. So since the boron and the aluminum have 4 bonds here, but they are okay with having 3 bonds because they are group 3, what they will tend to do is they will spit off an H minus. They will give up a hydrogen with 2 electrons. And so they serve as sources of H minus for these reactions. Both of these are sources of hydride, but they serve very different roles. Here's a table showing the type of functional group and the type of reducing agent, sodium borohydride or lithium aluminum hydride, and the resulting product that you get by using these reagents with these reducing agents. So aldehydes can get reduced by both sodium borohydride and lithium aluminum hydride. If you figure out how this goes, the H will attack the carbon, kick the electrons up onto the O. We'll have a carbon with 2 H's. The O will end up getting protonated. That's an alcohol. The lithium aluminum hydride will do the exact same thing. With a ketone, same thing. Hydride will attack the carbon, kick the electrons up onto the O. We're going to get an alcohol. Only if you start with a ketone, you get a secondary alcohol. The carbon bearing the alcohol has 2 R groups on it because we started with a ketone in both of these cases. If you start with an aldehyde, since there's only 1 R group attached to that carbon, you'll get a primary alcohol. So again, if you are thinking about your product and you say, okay, I want a secondary alcohol, you say, aha, I could make a secondary alcohol if I started with a ketone. Or, aha, I can make a primary alcohol if I started with an aldehyde. You cannot reduce alkenes in any case, but carboxylic acids or esters can both be reduced to primary alcohols with lithium aluminum hydride, but not by sodium borohydride. Essentially, lithium aluminum hydride is a stronger reducing agent. It is able to reduce carboxylic acids or esters, but NaBH4 is not. This is just a carboxylic acid that has been deprotonated. Since these are highly basic, the H- is a very strong base. They're showing this already deprotonated by the base. So here's a visual representation showing you the ease of reduction. The acid anion and the ester are fairly difficult to reduce, so they are only able to be reduced by lithium aluminum hydride, which is the stronger of the two. Ketones and aldehydes are easier to reduce, so they are able to be reduced by NABH4 as well as lithium aluminum hydride. Basically, the lithium aluminum hydride can reduce the crap out of everything. Sodium borohydride is a little bit more selective. This is important to know these things. For example, if you've got two of these groups on your same molecule and you want to react one but not the other, you can always reduce a ketone or an aldehyde if you use sodium borohydride. That will not touch an ester and an acid on the same molecule. That's it for lecture 1. The Stramanis workshop is Chem Activity 10, Chapter 10, Parts A and B. Keep in mind that your problem set is already due Monday next week. To study, I would recommend making a reaction map of transformation of alcohols. In Chem 304, I gave you my own handmade reaction maps for SN1 and elimination, as well as alkene reactions and alkyne reactions. I'm going to let you try to make these reaction maps for alcohols on your own. We're going to do more reactions of alcohols on the next chapter, so you can maybe combine the two into one big reaction map. Good luck.